Hi, everybody. This is our second lesson now of our remote learning. Last time we started talking about exponential functions. This time we're going to talk about those a little bit more. There's two kinds, basically. We didn't separate those kinds last time. The first kind of exponential is growth, and the other kind is decay. Then, lastly, the other new thing that we're going to talk about is there's a different way to write these exponential equations that are actually probably a little bit more applicable to what someone might use in real life. So, we don't want to waste any time. Let's get going. So, just a quick review of some important things that we need to remember from last time. An exponential function has x in the exponent spot. That's all an exponential function is. And I have an example here. F of x equals 4 to the x. X is in the exponent spot, so it's exponential. Something else that we need to remember is this was the general form of the exponential equation. We talked about that last time in depth. I'm not going to go back through what each of these letters does, the A, the H, and the K. We talked about that last time. If you are having trouble remembering what those do, what those mean, you should go back to the last video from last week and watch that over again. That's where you'll find that information. Okay, so the one letter that we didn't talk about much last time is B. And that's exactly what we're going to be focusing on today because B is what separates the growth from the decay. Okay, so here we go. This is going to be where we compare growth versus decay. For exponentials, I just put the formula back up here, the general equation up there, because this works for both. And I wanted to make that point that it's the same equation for growth as it is for decay. The only difference is B, and we'll get to what the difference is there, how B is different for each one. But first, let's look at the growth here. We're going to take a look at the graph. This is the same graph that we looked at last time. And we just kind of want to talk about what's its behavior. What is it doing? And last time we talked about how it starts out pretty flat, right? On the left side at the beginning, it starts out pretty flat, and then it starts to grow, right? And then it starts going up. And then it starts to go up faster, right? How fast is it going up? It goes up a little bit and then a little bit more. And now it's going up really fast at the end here, right? And so when it's going up really, really fast at the end, we're going to say that gets very steep. So it starts flat, starts to go up a little bit, and then at the end, it's going up a lot of it. Okay, some examples of where we see this kind of growth is with viral infections. Talked about how last time that's exactly relevant to what's going on right now with the coronavirus. This is why it is a concern, is because this is how this stuff grows. Also, bacteria, not just like infections, but like when your food gets spoiled, right? You get mold in your bread. Once that mold is there, even if you see a little bit, you should just throw it out because it's going to be in about a couple hours that you're going to see a lot of mold, not just a little bit of mold, right? It grows really fast. So as soon as food is spoiled, you should just get rid of it because it's only going to get worse really fast. Invasive species. So I don't know if any of you like to go fishing, for example, but if you go up to Wisconsin, and you take a boat up there, you have to wash off your boat before you leave. And then when you come back, you have to wash your boat off again because there's microorganisms and bacteria that are unique to each lake. And if we take bacteria from our lakes down here up to the Wisconsin lakes, it could run rampant and kill off the natural bacteria that already lives there and kind of ruin the lakes up there. So they actually care about that stuff a lot. Fire damage. It's like if your house were to get set on fire, if it burns for twice as long, you don't get twice the damage. You get like 10 times the damage, right? That's the way fire. So fire damage is this. You see this trend as well. And something that might be more interesting to everybody is money, right? Interest on any credit card somebody has. So somebody with a $10,000 debt is going to be charged a lot more interest than somebody with $1,000 debt. And so the more debt you have, the more interest you get charged. But it's not all bad. Savings accounts works the same way. So you put $1,000 in your savings account. First, it'll grow a little bit. It'll grow a little bit more, and once it gets really big, now it starts to make big jumps, right? So it goes good and bad when it comes to financial stuff that way. Okay, so when do we see growth? I want to tie this way back to the equation up here at the top, right? We see the graph, it starts flat, grows up, right? And so it's growing. and I want to tie this back to the equation. When do we see growth? And I said before, it's all about B. So we see this growth when B is greater than 1. Anytime that B up here is bigger than 1, you will see the graph grow this way. Okay, so how is that different from decay? We just talked about the growth. Let's talk about the decay. So behavior is kind of the opposite to the growth. It doesn't start out flat. It starts out very, very steep, right? It's falling very quickly. It's falling, falling, falling very fast. And then it starts to slow down, right? Here in the middle, okay, we're slowing down a little bit. And then it gets flat at the end, right? So the growth graph starts out flat. The decay graph ends flat. They're kind of like mirror images of each other. They are opposites. Okay, so opposite behavior between growth and decay. Now let's talk about some examples. Where do we see this? With car value. So you go buy a brand new car, and as soon as you drive off the lot with it, the price of the value of your car just went down about $1,000 or $2,000 immediately. And then the value car goes down a lot, down a lot, down a lot, but eventually it's still a car, right? So even once it gets to be like 12, 15 years old with 150,000 miles, it's still a car. And so you can still get, maybe $2,000 for it, $3,000 for it, whatever. But the longer you have your car, the value goes down, and it goes down just like this. It drops fast right away. Right away, the value of the car drops fast, and well, it's already pretty low, so you can't get any much lower. So, interest on loans. So this is really important. So you go buy a brand new car, right? And you probably don't have $22,000 to just pay for the car all at once, so you get a loan, right? And what you want to do if you want to save money on your loans is you want to pay extra money early, right? Because if at the beginning you still owe $20,000, that's a lot of money. So you're going to be charged a lot of interest. But by the time you get done paying for your car, now you're only I don't know, $500. And so when you only owe $500, the interest is very, very little. It might be a couple dollars. So really important tip. This is why this stuff is important. You can save yourself money when you're in a position to go get loans for cars and whatnot, that you can save yourself a lot of money by paying extra early. Because you can't, if the car's $22,000, you're going to pay that $22,000. But where can you save money? You can save money on the interest. And so you're better to pay extra early, and that will help with that. All right, last one is like digestion. So let's say you drink a cup of coffee, right? And your body, so this would represent the amount of caffeine in your body. At first you have a lot because you just drank that cup of coffee. Your body's getting rid of it, and then it slowly dies off. It's really not much there anymore, and so it kind of slows down. Okay, so this is where we see this. We start off with a lot. It falls very fast and gets flat at the end. Just like I did with the growth, I really want to tie this back to the equation. When does this happen? It's all about B. So what B numbers is going to make it fall like this instead of grow? And that's going to happen when B is between 0 and 1. So 0.25, 0.3. Any decimal or fraction that is bigger than 0 but less than 1. Okay, so just to summarize this really quick, growth starts out flat and then grows really fast at the end. Decay starts out high, falls fast, and gets flat at the end. So growth is flat at the beginning, decay is flat at the end. Growth is when B is bigger than 1. Decay is when B is in between 0 and 1 for this equation at the top. Okay. There are limitations on B. We can't have B be any number. I want to just bring it back to the simple form instead of looking at the big old form like this one right here at the top. Let's just go back to the parent function, the most basic form. So some number, and you've got x in the exponent spot. Remember last time we talked about that the domain for this kind of function is all real numbers. That means I should be able to put any number here for x, and there be no problems. I can put -1, I can put -1,000, I can put 23, it doesn't matter. I should be able to put any number here in the x spot and there be no problems, okay? But B can't be 0. Why is that? Well, let's look at just a quick example. Because if B is 0, and then I plug -1 in the x. Remember, I should be able to put -1 in the x spot. That should not be a problem. But if we have -1 here, remember the negative just means I'm going to take this number and put it in the bottom of a fraction. So that would be 1/0. But we can't divide by 0. That's not a thing that we can do. If you don't believe me, take any calculator, a real calculator, or the one on your phone, or just Google calculator. It'll pull up a calculator for you. Try to do 1 divided by 0. You can't do it. And the other thing is B can't be negative because all sorts of craziness happens if B is negative. For example, let's say that B is -2. Okay, no problem. Well, I can do -2 squared, and I should be able to do whatever exponent I want. -2 squared, well, that's 4. Okay, no problem. What if I make my exponent 3, though? So now -2 to the power of 3, that's -2 times itself 3 times. 2 times 2 times 2, and they're all negative. That's -8. So you can see what's going to happen here. Anytime that the exponent is even, we're going to get a positive. Anytime the exponent is odd, we're going to get a negative. So, I mean, you could graph that, but like you're going to be jumping between positive and negative, and it's not going to look nice. It's going to be all over the place because it's going back and forth. And then it gets even worse if we don't use a whole number in the exponent spot. What if I put 1/2 in the exponent spot? That should be no problem. But then what happens? Maybe you remember, we talked about this before. When we have 1/2 in the exponent spot, that means to do a square root. So square root of -4, okay, I can do the square root of -4. We've done this before. That's 2, and then I, because the negative on the inside. Square root of 4 is 2, and we need an I because of the negative inside the square root. So depending on what goes in your exponent, you get a positive number, a negative number, or an imaginary number. And because there's imaginary numbers involved, it's really difficult to graph this. You can't, because you have imaginary numbers and all. And when we do an XY graph, we don't use imaginary numbers on an XY graph. So B can't be negative. Okay, so we have a new way to express exponentials. First thing I want to do is, this is what we talked about last time. F of x equals A times B with the exponent x plus h, and then at the end plus k. So how does this work if you know the rate of growth or decay? What do I mean by that? You know the rate of growth or decay. So for example, if the interest on your savings account is 5%, okay, so that's something that you're gonna encounter in your life if you haven't already. You have a savings account and they say, okay, your interest rate for your savings account is 5%. It's not gonna be that high, but anyway, doesn't matter. It'll be some percentage. Okay, how does that fit into an equation like this? Well, it doesn't. We're going to use this different equation where we have g of t equals a, and then in parentheses we have 1 plus r to the t, and then we have a t in the exponent spot. T is our variable here, and I'll explain what's going on here. I'll go through each letter. So I'm going to stick to the savings account example to explain these variables. Okay, A right here would be the amount of money that you start with in your savings account. So you go and open your savings account, and when you open your savings account, you put in $100, $500, $1,000, whatever. You open a savings account. This is how much money you put in to start the account. And that's for just in general, the A is always like your starting value. It doesn't have to necessarily be the starting amount in your savings. A is going to always be whatever your starting amount is. T is time. That can be measured in days, weeks, months, or years, or any other unit of time. So decades, centuries, minutes, but those are less common. T could be measured in days, weeks, months, years, whatever. T stands for time, and that's our main variable here, and it's in the exponent spot, which is why this is still an exponential function right here. And lastly, R is the growth or decay rate. So whether you're growing or whether you're seeing decay, R is the rate. So that's your 5%, 10%, whatever. So R has a lot of details that go with it, or at least a few, and I want to make sure I clearly state those for you to help you out. For growth, if something's growing, then R should be positive. Okay, R should be positive. For decay, R should be negative. Or you could just do 1 minus your 10% or whatever. Okay, either R is going to be negative, or you're going to do subtraction instead of addition if you're looking at a decay problem. Lastly, this is really important. R often will be written as a percentage, especially in real life. And so in a real life, I'm talking about savings accounts. I'm talking about getting a loan for a car or whatever. Instead of using the percentage, instead of using 5%, 10%, or whatever, you have to use the decimal form. So instead of using 12%, you would put 0.12. Or instead of putting 7%, 0.07. By the way, it doesn't matter if you put the 0 in front of the decimal. I realized I didn't do a 0 here in the front. I did do a 0 here. It does not matter. Okay, but the easy way to sum up how do you get from percent to decimal is you just divide by 100. To get from 12% to 0.12, divide by 100. That's all you got to do. Okay. This is our last slide. Some important last notes. I put the big equation back up here that we talked about last time for a reason, and that reason is written right here. Everything that we talked about in the last video where we started talking about these exponential functions is still true. And I'm going to kind of go through what those things are really quick right here. So if you look at the equation, what each letter means and does, like A, what does A mean and what does A do? What is H and what does H do? What is K and what does K do? All those things are the same for growth and decay. It does not change. They do the same things, okay? Instructions for how to graph. So you're going to have a couple graphing problems where I say, hey, graph this function. The process is exactly the same. Step 1 is the same. Step 2 is the same. Step 3 and step 4, they're the same. If you don't remember what those steps are, just go back to the last video. It's right there, right? So for growth or decay, it does not matter. You do it exactly the same. The domain is the same. You should be able to plug in any number for x. So the domain is all real numbers, whether it's growth or decay. And how to figure out range and the asymptote. Also the same for both growth and decay. So if you need to brush up on how to figure out the range or how do I figure out the asymptote, just go back at the last video because it's the same no matter what. Okay. The thing that we're focused on here, the difference is between growth and decay. What we're focused on as far as how they're different is this right here. Growth starts flat and goes up. Decay falls really fast and gets flat at the end. And we're also focused on, for growth, B has to be bigger than 1. And for decay, B has to be between 0 and 1. Okay? So that's the quick summary of everything we just talked about. Okay? Well, that's all I've got. So hope you guys are still keeping healthy, keeping well, and I'll talk to you next time. See ya.